So looking at another optimization problem in calculus, we're going to try to find the largest possible volume of a cylinder. And we're given some information about the cylinder. We're given that it's inscribed into a sphere with a radius r. So that is inside a sphere of radius r. Okay, so let's draw a picture, or at least attempt. So let's say we have some sphere there. Think of it as three-dimensional. That's two-dimensional. And we have some cylinder in here. And I'm just gonna inscribe it in here, but it could look a little different, right? It could be skinnier, it could be fatter, but it's in here. And we're given that our sphere is radius r. And so if we take from the center, we know that out here we have some radius r. Well, let's think about volume. We want to maximize our volume. And so volume of a sphere. Let me just make sure I have it right. I don't know all my geometrical ones. Hold on. I meant maximize the cylinder and the volume of a cylinder. That is the pi r squared h. The thing in this case, though, is that I don't know, and it wouldn't make sense to me if this was equal to the same value of r as this one. So maybe let's call it a different r. Let's call the radius of the sphere piece, let's call that capital R. So this is going to be pi capital R squared times h. So some h in here. Okay. So there's a couple things we can do. We can keep it with these variables. We could rewrite it so that we can put this on what looks like the X or Y axis and name it variables that way. It's up to you. The one thing that you need to notice is that if we look at the radius r, I mean, I drew it for the sphere, I drew it here, but really, right, if we take the center and we go out, that would be radius r here also. Or I could come down here and this would be radius r right in here also, right? And so we can make a right triangle. Or if we want to do it this way, right, this would be r, capital R, and this right here. And so if this is my whole height, notice that this is going to be half of the height. Okay. So it really depends on how we want to write our right triangle to give us information. The problem with the volume that we're trying to maximize is that we have more than one variable in here, and that we're trying to rewrite this volume of the cylinder and just in terms of one variable instead of two. I'm thinking I don't want a fraction in here. And so couldn't we make this as, this is our capital R here. Let's make it a bigger triangle. So this would be right here. This would be 2R. This right in here, that's our height. And we know that this in here, well, one side, our radius here is R, plus our radius here is R. So our radius here is 2R. Okay. So we want to set up an equation we know, and because this is a right triangle, we now know that we can use Pythagorean theorem. And so Pythagorean theorem, we know that 2 little r quantity squared is equal to capital, or 2 capital R quantity squared plus h squared. So we have 4r squared, little r squared, is equal to 4 capital R squared plus h squared. So we either want to solve capital R in terms of h or h in terms of capital R. So we either want to solve for either one of those. I'm wondering if there's one that's easier than the other. Let's solve for h. That way we don't have to deal with fractions. So if we get h by itself, we get h squared is equal to 4 little r squared minus 4 capital R squared. And so we can take the square root of both sides and we get h is equal to, and it would make sense to have a negative length or height. So we're going to ignore the negative piece. So this is the square root of 4 little r squared minus 4 capital R squared. Okay. So we have our volume that we're trying to maximize, and let's rewrite that. We have pi capital R squared times h, and h is the square root of 4 little r squared minus capital 4, I'm sorry, capital 4 minus 4 capital R squared. Okay. So we want to go in here and we want to take the derivative of this. 1 second, let me just think about this before I go a little further. Okay, so I kind of made my life a little bit harder by the variable I decided to choose. And this is why, because notice that up here in my volume equation that I have this capital R squared in here. And so if I had plugged in what capital R was and squared it, I wouldn't have that radical anymore. And so let's kind of go back, sorry about that, and let's change what variable we're going to solve for. So we're going to use that same equation that we have right here. But we're going to solve for capital R instead. So I would have, in this case, 4 capital R squared is equal to 4 little r squared minus h squared. Divide everything through by 4. So I get capital R squared is equal to, well, 4 all over 4. So that's 4 little r squared minus h squared all over 4. So now when I take the square root of both sides, I get capital R is, and we're again thinking just positive, is the square root of r squared minus h squared all over 4. So rewriting this, our capital R is this right here. So let's go again and plug that in. We got the square root of little r squared minus h squared all over 4. But they tell me that I'm going to square that term and then times this h. So our volume of the cylinder is pi. The square root goes away, but we need parentheses still. So it's r squared minus h squared all over 4 times h. So we're going to take the derivative of the volume with respect to h. Remember, r is a fixed radius. They didn't give us what it was, but it's a fixed radius of a square of the sphere. And since r is a fixed number, when we take the derivative of r, we're going to treat r as a constant. But before we take the derivative, it would be easier if we first distribute. So let's distribute pi h to both terms. So pi h times r squared. So this gives us pi r squared h minus pi h times h squared over 4. So that's going to give us a, how about pi force h cubed. Okay, so let's take the derivative here, dv dh. So the derivative of pi r squared h, that is just going to be pi r squared minus, and the derivative of pi force h cubed is 3 pi force h squared. So we're trying to find when this is equal to 0. So we're looking at when is pi r squared minus 3 pi force h squared equals 0. So I'm solving for h. Let's add 3 pi force h squared to both sides. And so we have 3 pi force h squared equals pi r squared. Get h by itself, we can multiply by the reciprocal of this coefficient in front to both sides. So let's multiply both sides by 4 all over 3 pi. So we're left with h squared is equal to, well, the pi cancels, and we're left with 4/3 r squared. So h, taking the square root of both sides, I get the square root of my numerator, 4r squared is 2r, all over the square root of 3. And again, we're just looking at positive because it doesn't make sense to be a negative. Okay, so we're almost there. We have to figure out, we wanted the dimensions and we want the maximum volume. And so we have our height. We need to figure out what the radius of the cone is. And then we can plug that in here to figure out what the maximum volume is. One quick thing, again, we need to make sure that this is a maximum and not a minimum. And so we could look at the second derivative, or we can use the first derivative test. Well, let's look at the second derivative. It'll be much faster. So if I look at the second derivative here, the derivative of the first piece, pi r squared, that's just a constant. So that's 0. And this is equal to then minus the derivative of 3 pi force h squared. So the derivative, and this is with respect to h. So bring down the 2, we get 6 pi force h, and that's negative. So if we plug in this value of h in here, notice that you're going to get a negative number. And so the double derivative less than 0 is going to be a max. So a max does occur here. And again, we want to find our dimensions, so we can plug it in. Capital R, this is equal to the square root of little r squared minus, we're going to square this piece all over 4. So if I square my h, that gives me 4r little r squared all over 3 divided by 4, which is the same thing as times 1/4. Just give myself some more room for now. So notice your 4's cancel. These technically are like terms. Let's get a common denominator. So this would be a 3 little r squared minus little r squared over 3, and we have the square root of that. So this is 3r squared minus 1r squared. That is so square root of 2r squared all over 3. You can clean it up a little more if I wanted. 2 root 3 times little r. A lot of times we don't like radicals in the denominator. And I guess I kept it over here, so let's just do it. So square root of 2 all over the square root of 3r. So let's go back to the volume of our cylinder, and let's plug in our values in there. So we have pi all times capital R squared, which was root 2 little r over root 3, all squared, times h, which was 2 little r all over root 3. So cleaning it up a little bit, squaring square roots, those cancel. So that gives me 2 capital R squared over 3 times 2r over root 3. So our volume is equal to 4 pi r cubed all over 3 root 3. So really, this would answer now any question if we were given what our radius of the sphere was. So if it told us our radius of the sphere was 4, all we could go in here and plug in 4 for little r and figure out what that maximum volume of the cylinder would be.